My name is Vivek Subramanian. I was actually a postdoc with Professor Hu. And one of the things you probably noticed as we reached the end of the day, now again, we've had talks on devices, we've had talks on advanced materials, we've had talks on various aspects of design as well. And many of these talks are from Professor Hu's former students, and in my case, I'm a former postdoc. One thing I would like to say, you'll notice that all of those show a certain character of Professor Hu's training for all of us. When I got to Professor Hu's group, I was an experimental jock. I like building things. And I learned that from Professor Hu, one thing I really learned was the importance of the math. In other words, it's really important to have sort of fundamental physical understanding of what you're building. And I think every single talk that you've seen today shows you that. And I will personally say, at least for me personally, that mentorship came from Professor Hu, very much so. So now, having said that, I think let's start with the first talk, which is from Boon-Khim Liew, who is also, of course, a former student of Professor Hu. He received his PhD in 1990. And he's currently a senior manager in the advanced technology group at Nvidia, where he's responsible for working with foundry partners to develop technology and accurate models for simulation. And before Nvidia, he was with Cypress, BTA Technology, TSMC, and SMIC. Now his talk is entitled Challenges in Sub-20nm Design.
Thank you. I think before I start, I have a few stories to share too. I think these are very good stories. I think as I share the same experience as the feelings of Klaus, who spoke earlier about the influential persons in his life. I'm too greatly, I think, benefited in interacting with Professor Hu, and actually I was I think very fortunate being his students and later being his first employee in BTA. So I want to share a few of my experience, and these are the inflection points actually in my life. And I guess besides my parents being influential persons in my life, I think Professor Hu is the next one, and of course there's another present one. So I think my first inflection point would be sometime, I think in the first or the second year of my graduate study. So I picked up this topic of electromigration. And at that time, the industry was interested in looking at the electromigration lifetime under AC conditions, not under the pure DC condition, because circuits, as you know, operate under AC conditions. So I picked up that topic, went to the lab, built a lot of this high AC current sources. And I'll explain to you why we need really high AC current sources. So went to the micro lab, which is a great experience. We just sputter the lines and play around with the tool. You can actually change the target in the sputtering machine yourself, make the mask, and then pattern the aluminum lines on the wafer. So went to the lab, put these lines to stress, collected a lot of data, and initially what we found is like the lifetime for this metal line are pretty long under this AC conditions, and we really need those high current to get the lifetime data. So we collected a bunch of data. And at that time, I was very puzzled. How can we explain the enhanced lifetime under AC conditions? So Professor Hu and I think we discussed for a few weeks, and still it's a puzzle to us. What kind of model can explain that? Until I remember at one day, I think when Professor Hu pointed out to me that, well, why don't you try the relaxation model? As you know, the relaxation model has been very common in looking at the device physics, all the device phenomena. So, and then I went back and then tried it out, wrote a few equations, doing the differential equation, integrating equations, and then we come up with a model. And the model, the nice thing about the model is not only explains the DC case, the pulse DC case, and also the AC case. And that model went later to the BERT, the Berkeley Reliability Simulator. So that became the main topic for my thesis research. So that was the one first inflection point. Now the second inflection point came when after I graduated, after working for a few years in the industry, and in 1993. So I talked to Professor Hu, Professor Ko again, and we decided we wanted to start a company to commercialize the modeling, the BC modeling software, as well as BERT. Okay, and in 1993, May, I think Zhihong was most responsible for the technical development for the softwares. And we started our first demo at the CICC in 1993. Okay, and that was another inflection point with the positive results. And another experience which I also remember for stay with me is the experience at the end of around 1993. So when we started a company, we got the funding. I think Professor Hu chipped in some of his own money for to invest in the company. We got an outside investor, and then we kind of divide the money up. So some of the money would be which I would use for the day-to-day operations, paying the payroll, buying PCs, hiring people, and all those stuff. And then we decided to also set aside some money that is going to be for rainy days. Okay, and I think towards the end of 1993, the money in my account, the account that I'm responsible, is running out. And in about a week, I need to pay people. So I was very worried about what happened to the payroll. So the payroll would stop. So I called Professor Hu. And then, and of course, feeling a bit embarrassed at that time because when we started the company, I had a great business plan. Within 6 months, which we should be selling software, collecting money. It's a very naive engineer talk, right? You do not account for the account receivable. That means your software, you ship the software, but people are not going to pay you right away. So fortunately, I think after talking to Professor Hu, I think the next day, my account, he wired money into the account and used some of the rainy fund. And then I think ever since then, we never use that fund in that account anymore because revenue started coming in, and then the company prospered. And my last experience I want to share with you is actually at the end of 1995, I decided to pursue other interests, meaning I want to leave BTA to go to join TSMC in Taiwan. And of course, it was very difficult for me at that time to send my resignation letter to Professor Hu at that time. So it was a difficult moment, but I talked to Professor Hu for a long time, and got his blessing. He actually said, "Well, TSMC is a good company. You should go." Right. So of course, at that time, I didn't tell Professor Hu that I actually met my other influential person in Taiwan that I had to go. But he found out quite soon later on because he actually was my.
You invite me to your wedding.
Yes. So I just want to share those stories with you. I think those actually has a very good positive outcome. I think most of you also have had that positive experience. And we gather here today to celebrate, as we celebrate Professor Hu's birthday, celebrate his life. It also reflects back to us that all the positive things and outcomes that we got from meeting such a great person. Thank you. Okay. Now with that, I want to start my talk. And so the first thing I'm going to do is actually, instead of going to the slides, I want to show you a demo program. Okay, and this demo program is very relevant to the audience here, particularly I think to Professor Hu's research team. So this is a program, simulation program, that is simulating the electrons and holes inside. As you see the structure, I'll turn it around so you can see what it is. FinFET. Okay, and this program is running actually on the CPU chip on my laptop. Okay, it's not a complete program, but it's a demonstration idea what we can do with a GPU technology. Okay, so the structure here, as you know, the light blue one, that's the source drain, and then in the middle joining it, you have fin, and the black, the dark blue is a gate that's wrapped around the three sides of the fin. Okay, so what I want to turn on is another view, and this is the electrons and holes in the FinFET structures, okay, at equilibrium. So at equilibrium, you can see there are a total of about 5,000 electrons and holes inside the structures. They are moving around, okay. So this program is just of course, as you might expect, the channel is close to depletion. Most of the electrons and holes are on both sides of the source drain. Okay. Now, what I want to point out is as the simulation program is calculating the electrons, the movement of electrons in the structures. Okay. Now, the calculation, for example, at this point, right, it depends only on the potential and the electron concentration in the vicinity of that electrons, and so are the other locations in the structures. So what this means is this simulation can be broken up into many pieces, and if you run the calculations, right, in parallel, you can speed up the simulation for this problem. And this is what, in fact, is the GPU is doing. The GPU in my laptop, it has 48 cores, but you can see that it can handle 5,000 electrons and holes quite well. Okay. Now, the problem of doing the simulation is not very different from rendering graphics in a PC or laptop. Okay. As the program is drawing graphics in this region of screen or this region of screen, it can be done in parallel. Okay. So the number of processing cores that's available to you would really speed it up the calculations. Okay. And that is why GPU chip is well suited for high performance computing. Okay. Now with that, I want to introduce to you one of the most advanced chip that we make at Nvidia. This is the chip, the highest performance chip that we made today. It is in the product we call a GPU accelerator, which is the hardware that is inside the world's fastest computer today in the US and in the world as well. Okay. This chip we codename is GK110. It has 2,688 processor cores. And the computation performance for this chip is 3.95 teraflops. Okay. And as a comparison, the x86 CPU per core, the performance is about 12 gigaflops. Okay. Now, what's most amazing is the power consumption. This chip, operating at the full power, is consumed 235 watts. Okay. Now, a comparable performance using maybe 300 x86 CPUs would consume 3,000 watts. Okay. And this is a power saving of 10x, more than 10x, actually. Okay, some statistics for this chip. This is manufactured using the 28 nanometer high-K metal gate technology. It has 7.1 billion transistors. But the most amazing thing is to connect all these transistors, it has more than 20 kilometers of minimum width metal lines, more than 10 billion contacts, and more than 10 billion vias. So it's quite amazing that we can make this chip. Okay. So with this, I want to go into the main part of my presentation to talk about what are the requirements and challenges for sub-20 nanometer design. Okay, I give you 3 here, but actually there's a 4th one. Okay. They all conveniently start with P. So the first one is performance. Okay. Second one is precision. The third one is perfection. I'll go through all this. And actually, there's a 4th one. It's also start with P, price, which I will not cover here. Okay, let's start with the performance. How do you evaluate performance, the chip performance? As I alluded earlier, the higher the number of processing cores available, and the faster those cores running, right, you get higher performance. Now, in device, well, most of us are device physicists and also engineers. So the equation is very simple. The performance normalized to the chip area is equal to the gate density transistor, how many transistors we can put per millimeter square, times the circuit speed. It's very, very simple equations. Okay. Now I want to look at the transistors density and the circuit speed over different technology nodes. As is, the first one is the density of transistors from 90 nanometer down to 20 nanometer. And, the vertical axis is normalized to 40 nanometer technology. Okay. So as you can see, the transistor gate density increases very nicely over the different nodes. Okay. And I want to point out one thing here is that if you notice a little bit the curvature of the curve, from 90 nanometer to up to 28 nanometer, the gate density actually increased close to a factor of 2 for every main node. From 90, for example, from 90 to 65, and then 65 to we don't have 45, but then 40 nanometer. But from 28 to 20 nanometer, this scaling, although the feature size scale, the gate density does not increase that much. And actually, it's somewhere between 1.5 to 2, closer to 1.5. Okay. Now, although the feature scales, they are more restricted design right now because of lithography patterning issues. So we do not gain that much in the transistor density. But still, we have quite a nice curve. Okay. Now, the next term in the equation is the circuit speed. Okay. Now, I plot the circuit speed for let's say, inverter ring oscillator, okay, at constant power. Okay. Now, this speed is, because of the transistor scaling, it also goes up about 20% for every node. Okay. But for GPU design, the circuit speed requirement, we have to make some adjustment in consideration of power. Now, the reason is this. This curve, this dash curve is arrived at a constant leakage current per micron. Okay. But as we pack more and more devices or transistors onto the chip, the power will increase. In order to keep the power, maximum power for the chip constant, we need to reduce the power per gate by raising a VT a little bit to reduce the leakage, and also lowering lowering the VDD to reduce the dynamic power. So the curve that we use in calculating this performance equations is actually the adjusted curve. The speed at constant power per millimeter square. Okay. Now this, as I said, you increase VT, reduce VDD, your speed is going to be compromised. The performance is less. And this curve becomes flatter. And I should point out at this point is the data in this graph are all based on planar CMOS technology. Okay. So from 28 to 20, you can hardly see any speed gain at this constant power density. So if you multiply these two together, you get the performance per millimeter square curve under the constraint of power. Okay. And this curve is going up nicely. And you, as you can see immediately, it's mostly due to the transistor's gate density increase. Okay. So we are hitting roadblocks in the device scaling in terms of speed improvement. And of course, the invention of FinFET greatly boosts the performance, and which I'll talk a bit later on. Now, I want to share with you another thing that we do to fine-tune the performance by trading off speed and power. Okay. Now this curve, there are three curves on this plot. They are the red and the white curve actually represent the window of VDD that we can adjust. And actually, we adjust it dynamically in our chip, depending on the user experience, what the user is doing. Okay. Now, the top curve, that's a Vmax. That's the maximum voltage we can operate the chip because of limited by power and also reliability. Okay. And this Vmax is coming down as we scale the dielectric. We run into more device reliability problem. And the Vmin, the Vmin represents the minimum voltage that we can operate, that the logic function still works in a chip, and it is limited by two things. First, as I alluded earlier, we increase the threshold to reduce the leakage. So lowering this Vmin, we will run into the voltage headroom issues. So we cannot lower that much. Okay. Now, another more serious problem is actually due to the threshold voltage variations. Okay. The threshold voltage variation would actually affect the operations of the memory, the SRAM, and also sometimes in the logic. Okay, that we cannot lower the Vmin that much. But the key message here is that the window that we can adjust this VDD to fine-tune the speed and power is getting smaller and smaller, okay, for planar CMOS technology. And that is why this mighty transistor called FinFET saved the world. Now, I copied this IV curve from the Intel website, but I just want to give you some idea how from a design perspective, when we look at this kind of IV curve, what do we see in it, and how do we use it? Okay. Now, the black curve, of course, that is from the planar device, and the FinFET device is the blue curve right here. And notice it has a much a steeper subthreshold slope, okay, which reduces the leakage when the gate is turned off. Okay, but for us, as we face the roadblocks of Vmin and power, so what we want to do is actually shift this curve, as is shown here. Shift this curve to lower the VT. Okay, and you get the same I-off, but now your VT is lower, which means you can lower your VDD and yet still be able to get the same performance. At the same time, you lower your dynamic power by a lot. So next, I want to move into the part about the precision. I want to talk a little bit more about variation in this slide. So this is a slide showing the impact of 1 nanometer L-gate variations to the performance of our chip in speed and leakage. Of course, the 1 nanometer larger, the speed is going to get reduced. And 1 nanometer smaller, the power is gone up a lot, as shown here in the red curve. Okay, so you might ask the questions, well, wouldn't you only have one direction in the movement of L-gate? That means if the L-gate for all the transistors in the chip move in one direction, right? Then why not you bin your products according to power and speed? And that's the ideal case. I think as Zhihong pointed out, the local variation is the part that's affecting us. Because on the chip right now, this 1 nanometer variations is happening within that chip. Okay, so the window actually which actually represented by this orange curve here, the bin yield loss, because we bin our speed our products for power and also for speed. And when you have variation of power and speed, some of these chips is going to go outside that bin. And we can see that this is a real data. We can see that in the production today. 1 nanometer really would kill about 10% of yield for at 28 nanometer. Okay, and I should point out that you see a little bit that this curve is kind of leveling off from 40 nanometer to 28 nanometer. Maybe you say, well, there's a relief. Well, the relief comes at the expense of performance, because from 40 to 28 nanometer, the L-gate device, the device L-gate did not shrink that much. Okay, and that is causing this leveling off of the increase in power and speed. Okay. Had the L-gate be shrunk to 20 nanometer, okay, this curve, 1 nanometer for power increase out from our prediction or simulation, would increase power by 50%, the 1 nanometer. Okay. And the speed variation will be 5%. Okay. So another thing that I want to mention is the layout effects, which also Zhihong presented earlier. This is a systematic effect. Okay, I explain a little bit about this. So the transistors, in this case, this one, the DUT, labeled DUT, the VT and ID set depends on the distance to a neighboring transistors, as indicated by ODXX on both sides of transistors. Okay. Now the dependence is highly nonlinear, as shown by this curve. Okay. You can see for small spacing, ID set for the FinFET, the blue line is increasing, and then after that it decreases. For PFET, it starts out decreasing, and then it started to go up, and that can be explained, I think, physically, because the STI shallow trench isolation between the transistors are filled with different materials. So they have the liner materials and have the fill materials. And these two materials have different mechanical properties. So depending whether you have a small spacing, which is more, the strain is going to be dominated by the liner, or you have a large spacing where the strain is going to be dominated by the fill material. Now this effect is very highly nonlinear, as shown by this curve. Okay, and it changes from time to time. It depends on the conditions where you deposit this first, and also the temperatures annealing that's carried out after the deposition. Now this layout effect widens the corners, the variations for the best and worst case sender cell delay and power. So I want to explain a bit more about that. In our place and route design flow. When we place a device, an inverter, for example, this inverter here, we do not have a knowledge beforehand what is going to be placed beside this device. Okay. So as when we place that center cell, okay, and we want to know the timing and the power of that center cells, we will have to build into the characterization, the center cell characterization, the worst case layout effect that this transistor can see. Okay, so that's why the standard cell power and timing corner will get wider on top of our normal process voltage and temperature corners. So even the model can be very accurate to model this effect, and even the FET can produce this device time over time, the same characteristics. It still hurt our design. Okay. And now another example of the precision that we need in the control of critical dimensions and overlay. Okay. I'll show a layout of our inside our chip. The green one is the matter 1 line. Let me see. Okay, this is the green matter 1 line. Purple is the matter 2, and joining the green and purple is a veer in blue. Okay. Now the problem here is actually caused by this veer to this matter 1 spacing. So if we do a cross-sectional cut along these directions, okay, this is what we'll see in this picture. So the veer 1, and this is the matter 1. As you know, the process is not always precisely placed. Okay, the veer 1 is extended slightly beyond the matter 1. Okay, and this is an issue because there can be a risk of TDDB breakdown between veer 1 and matter 1. Okay. I think quite a long time ago, we studied about the gate oxide reliability for 20, 30 nanometer kind of dielectric. Here today, we are studying the TDDB breakdown of low K dielectric of about 20, 30 nanometer. Okay. And what are the key factors of control here? Okay, it is the matter 1 CD, okay, the CD variations. Okay, this distance depends on that. The veer 1, the bottom veer 1 bottom CD, and lastly the veer 1 to matter 1 overlay error. Okay, and it turns out the last component is the one that's the most difficult to control. Okay, which brings me to the next slide. Okay, this is a calculated chip failure rate, okay, in parts per million as a function of the veer to matter 1 overlay error in the sigma. Okay. Now the assumptions is here in the blue box. So we assume some CD variations of matter 1 CD and veer CD. And I want to point out to you that this curve is in log scale is changing very fast. And notice the scale on the horizontal. This is a 10th of nanometer. Okay, so at an overlay of 2.8 nanometer, 1 sigma, practically kill this chip. This chip will have no yield. Okay, but if we can improve from 2.8 to 2.1, we can probably have a good yield. Okay, it's a difference of tens of nanometer, small dimensions. Now, finally, I want to talk about the perfection in the manufacturing process. So this example is an example of veer defectivity and how it affects the yield. It's plotted on the vertical axis. I'm showing the different technology nodes, okay? And since we have a different number of vias in each technology node, so the sensitivity of a different node versus the defect level, okay, is changing. So as we have more and more vias, 10 billion vias at 28 nanometer, we really need a defect level of DPPB, defect per billion. Okay. Now, 1 DPPB, as indicated here, is this line. Okay. Now, for a chip, 28 nanometer, if we don't do anything, you can see that the fab has to really go down to maybe 0.1 DPPB in order that we get yield. Okay. Now, of course, designers are smart. So we practice a DFM. So the DFM that we do is we put redundant vias. And sometimes, a lot of times, we substitute single square via with rectangular via, a larger size via. Now, even if we do that for 20 nanometer, instead of a 10 billion single vias, we still have millions, actually hundreds of millions of single via that we cannot replace. And in order to make the chip yield, we still need a DPPB close to 0.5. Okay. And this is what I call perfection. Any defect that less than 1 DPPB is close to perfection. Okay, this is my final slide. So I just want to reiterate again the 3 Ps that we require and the challenges in the design. The first is the performance, as measured in transistors, gate densities, transistor density, the circuits, and the circuit speed under the constraint of power. Next, very important, is the precision in the SPICE modeling, in the control of critical dimensions and also overlay. And finally, we need a perfect manufacturing process with very low DPPB to get a good yield. Thank you for your attention.